Before we look at the differential equations governing LRC circuits, let's try to develop at least a little bit of background and intuition related to capacitors and inductors. So a parallel plate capacitor will consist of two plates. Imagine this is a metal plate. We're looking at it edge on, so let's see, let's get oriented. Okay, there we go. Okay, so here's one plate, here's another plate. We've got a source here that pushes positive charge in this direction or pushes negative charge in this direction. Now, if it's a positive charge is being pushed around, then this positive terminal will push positive charge onto this plate of the capacitor. And where's that positive charge going to come from? Well, it has to come off of this plate. So it moves charge, positive charge from this plate through the circuit onto this plate. Now, in a circuit involving metal wires and metal components, more likely it pushes negative charge this way, in which case it pulls negative charge off of this plate and pushes it onto this plate. Either way, you end up with positive charge, a positively charged plate here and a negatively charged plate here. Now, going back to the Gauss's law idea, we construct a rectangular box around this plate, and we see that the positive charge results in electric field pushing away from the plate. Over here, same thing, we have an electric field, but it's pushing inward toward the plate. And I realize this is kind of smudged here. Let me see if I can make it a little clearer. Okay, these arrows should be pointing inward. Kind of small, might be a little bit hard to see, but hopefully you understand what you're saying. And if not, review what we've already done. But the result is electric field from this plate, between the plates, it's in this direction. Okay, on the other side of the plate, it's in this direction. And electric field from this plate, which is between the plates in this direction and outside the plates in this direction. Not sure I improved anything up here. That should have worked. Okay. The fields from the two plates then reinforce between the plates and cancel out on the other side of the plate. So on the right of this plate, you have a field pointing this way from this plate, and this plate results in a field pointing this way. The two cancel out, and something similar happens on this side of this plate. So you get a reinforced electric field between the plates. So what we have then is pretty much constant electric field perpendicular to the plates. The field is constant because as long as you're closer to the plate, a lot closer to the plate than you are to the edge, the field doesn't dissipate as you move away from the plate. So we have a constant electric field perpendicular to the plates. The electric field is proportional to the total charge Q. Q is the magnitude of a charge on a plate. On this plate or this plate, the two plates will have charges of equal magnitude, so that the greater the charge on a plate, the more charge you have enclosed in this little box, and the greater the electric field. And it's all direct proportionality. Now, if the plates are separated by a distance d, then your voltage is equal to your electric field multiplied by d. Remember, the electric field is the force per unit charge. The voltage is the work done per unit charge. If you multiply the force by distance, you get the work. So if you multiply force per unit charge by distance, you get the work per unit of charge, or the voltage. So the voltage across this capacitor is just the electric field times the distance. The capacitance of the capacitor is the amount of charge you get per unit of voltage, per unit of potential difference, and I'll just use voltage. So it's charge over voltage. So a bigger capacitance will hold more charge for given voltage. Now, if you increase the size of the plates, that's going to distribute your charge Q more widely. You're going to have less charge per unit area, so there's going to be less charge inside each of these little boxes, so you're going to have less of an electric field. So bigger plates are going to give you less of an electric field, which gives you less voltage, which gives you a smaller denominator here for the same amount of charge, and therefore a bigger capacitance. So bigger capacitance would be associated with bigger plates. We're going to do all this in more detail, so you don't necessarily have to understand every detail of this, but if you do, it's going to really help you later on. So I recommend it, but don't get hung up on it at this point. Okay, so that is charge per volt. Okay, amount of charge you hold per volt, and it follows then by simple rearrangement that the voltage is equal to the charge over the capacitance, and it's the voltage that goes into our differential equation.